Okay, mine says allow closed captioning to record this meeting, and that's what I want, right? So I had yes. Okay, so I guess I'm good.
Yeah, I see it. It says recording.
All right, very
Egg
good.
on my face.
I see it as well now.
Okay, good.
I see
Good.
too.
Awesome. Okay, so we're talking about limits today. And so the first thing we're going to do is something simple. So we're going to call this example 1. And this is called limits, finding a limit. So basically, in this case, I have y equals, or f of x equals x squared. So if you think about x squared, it's basically a parabola. And it's centered about 0, 0, going up on either side equidistantly. It says find the limit as x approaches 2 for f of x. So if you notice, as x approaches 2, so 1, 2, we're going to go 1, 2, 3, 4. And obviously that point is right here. And you can see that the value is, you know, the limit is as f of x equals approaches 2, it equals that. If you look at it from the limit as x approaches 2 from the left, f of x is approaching also. It's also 4. And as x approaches and the limit from the right, it also approaches 4. So I assume that was pretty easy for you to understand. Or is there anybody who needs clarification on that? No, you're clear. Okay, good. All right, so then what happens in example 2? In example 2, I have find the limit, and we have a g of x function. And this function is g of x as x squared minus, or I'm sorry, x cubed minus 2x squared over x minus 2. And they're asking the limit as x approaches 2. So there's a limit of the function as x approaches 2. So what you want to know here is that as x approaches 2, we end up with 4. And as straight as that may sound, if I take x squared, let's factor the top part. If I take x squared out, I'm left with x minus 2. And this is over x minus 2. So you're back to it's x squared. So as the limit approaches 2, this equals 4. And same thing goes for from the left or from the right. Now, if I show you this next example, this is example 3, this is a little system. So it's got a system. You got a limit as x approaches 2 for h of x. Now h of x is a system of equations, or is a system. It has x squared, and this is if x is not equal to 2, or it's 1 if x is equal to 2. So we call it a piecewise function, basically. So if you notice in this case, you have the following. You have the same x squared. More than anything, get to know the semantics. So you've got the system that goes like this. At x is 2, you've got a hole, and then it continues. So in this case, you want to say that you have a limit of h of x is equal to 4 when x is equal to 2. But as it approaches 4, it gets closer to 2 on both sides, right? So in this case, h of 2 is actually equal to 1. So if we consider this, in a sense, a whole. So in this case, you would have a point. Let's say this is 1, and let's say this is the point where x is 2. At this point, we would have 2, 1 as a value. Does that make sense?
Yes.
Okay. All right. So let's take a look at example 4. In example 4, we have the limit as x approaches 2 from the left for f of x is equal to 3x plus 2 over 2x plus 4. So if you look at this one gets tricky because if you were to draw an f of x type table, so let's go ahead and draw that. Let's go ahead and pop in where x is negative 2.1 and negative 2.01 and negative 2.001, 0.0001 and negative 2, and I'll stop there. And let's plug it in and solve. So if you take a calculator or whatever system you're using, and we say, okay, well, 3 times negative 2.1, okay, and that plus 2, divided by 2 times negative 2.1 plus 4 gives me a value of 21.5. Do the same thing for this one. So we will start 3 times negative 2.01 plus 2. Get that value. You're going to divide it by 2 times negative 2.01 plus 4. That gives you 201. Let's go with 0.5. And we'll do the same thing here for this one. You're going to plug it in. Obviously, you could tell that the numbers are moving. So this is going to give us 2001.5. And then you get to negative 2 itself. And there's no value that fits in there. And you would say in this case, this is undefined. Okay, undefined. So this is the same, I think, as if we're going to come from the right versus from the left. It's undefined regardless. So this does not exist. Does not exist. So if we were to graph this, let me show you what it looks like. And so I'm going to pull up. You should be able to see my screen going to Desmos. Okay, and so here's we have parentheses 3x plus 2, close parentheses, divide that by 2x plus 4. Close that parentheses. You notice what you have are trying to get it to. Oh my God. Oh my God. Okay, what is that? That's pretty cool. All right, not what I need. Okay, let me get out of here. Obviously, I had something that's obviously weird. Okay, let me try decimals again. All right, sorry about that. So this is equal to parentheses 3x plus 2. And this is divided by 2x plus 4. And you can see that you have this weird figure. Obviously, you have two points here. That's lovely. And it looks like at x is equal to, let's see, -2? -2 or +2, regardless of how I approach it, it just doesn't exist. Do you understand what's happening here? Do you see how where I have a value here, where if I go with x equals -2, for example, that's asymptotic. That's no good. That is definitely a point. And it looks like at x equals 3/2, or y equals 3/2. So y equals 3 divided by 2. See, it also has that as an asymptote. So it looks like if you look at it carefully, it just does not exist. Is that clear?
Yes.
Is it making sense, everyone? Okay. So let me go back to my other function here. So there you can see how it does not exist. I showed you the picture for that. All right, so that's example 4. Let's look example 5. Again, this is all about limits, all right? So this one, you're going to do the limit as x approaches 0 for the absolute value of x over x. So if you look at a graph, again, say you have x and f of x, and I'll take it to the middle. Let's substitute it -0.1. Let's substitute 0.01. -0.0001. And let's go with 0. That's a halfway point. Obviously, from the right, you're going to go 0.0001 and so on. So if you plug it in, sorry. So you plug in -1, -0.1, you're going to get -1 for y. And same thing goes for the big one. for the 0.01. And negative 0.0001, same thing, you get -1. Same thing over here, you will get +1. So, but the thing is here, there's nothing. In this case, you would say it does not exist. So you know this is true because the existence of the value may not exist, and you'll know that because if it becomes too large, so for example, it becomes infinite, or it becomes too minuscule, it's just too different a value to calculate. So let's take a look at the existence of limits. So the existence of limits, and so for example, the limit of the function as x approaches a value, so let's call it a. Let's call it a, and that may not exist. Okay, and that happens when, number one, you know that that happens when if f of x becomes indefinitely, so it becomes infinitely large, in magnitude, and you say that is whether positive or negative, and in this case, as x approaches, the number a, so we'll call it a, from either side, and we say in that case, the limit does not exist. And usually I write DME, it does not exist. So in this case, the limit of x approaches a for some f of x is equal to infinity. You can also say the opposite, which is b, which would be if the limit x approaches a for f of x. In this case, negative infinity does not exist. So, the second point I want to make is if the limit as x approaches a for some f of x function is equal to the limit, and that's what L stands for, and the limit as x approaches a, in this case from the left, in this case from the right, of some f of x is equal to m, and L does not equal m, you also have a situation where the limit does not exist. All right, so let's take a look at some rules for limits. Or we can talk about the rules. Any questions on this so far?
No.
No? Okay, let's take a look at the rules of limits. So the rules for limits. I can do them with examples as we go, or I could do the examples first. I don't know. I think I'm gonna go. It's only one of a few of them. There's 10 rules. So let me do the 10 rules. So let A as a limit, A as a number, and B as well be real numbers. And let F and G be functions. Such that the limit of x approaching A for f of x is equal to A, and the limit, so and the limit of x approaches A for g of x is equal to B. Okay, so let's start with that. And rule number 1, if k is a constant, I'm sorry, it's constant, then consider the fact that if we have the limit of k x as x approaches A is equal to k. So that's one rule. I'm taking the bracelet off. The second rule is if k is a constant and you have multiplication, you have the limit as x approaches A, and that is equivalent to k times f of x, which is equal to k times the limit as x approaches A for that f of x, and that is equivalent to k times A. So that deals with multiplication. If you're dealing with differences, addition or subtraction, so in this case, the sum or difference So this is the rule for limits, obviously. In this case, if I have the limit as x approaches a for some f of x value, plus or minus some g of x value, then the limit of x approaching a of f of x plus or minus the limit as x approaches a for g of x, and that is equivalent to a plus b. Now, the product rule for limits. So this is the product. This is the rule. These are all rules, by the way. So in this case, the limit as x approaches a of f of x times some g of x that is equivalent to the limit as x approaches a of f of x times the limit as x approaches a for the g of x and that is equivalent to a times b. Now, number 5, which is a quotient rule for limits. So in this case, you have the limit as x approaches a, and you got f of x divided by g of x, and that is equivalent to the limit as x approaches a for some f of x divided by the limit as x approaches a. This is true for g of x, and that is equivalent to a over b, so a divided by b, so long as b is never equal to 0. Okay. Number 6 is the polynomial rule for limits. So in the polynomial rule for limit, you're going to call p of x the polynomial. So this is equivalent to the polynomial. And that comes to the limit of the as x approaches a for some p of x is equal to some p of a. And I'll show you examples of that in a few.
Excuse me. So pretty much for polynomials, you can plug any number.
Yeah.
And then it will get you the answer, right?
Pretty much.
Okay.
So in the power rule, you're looking at the limit as x approaches a of f of x. And this is to the kth power. Now, this becomes the limit as x reaches a for the f of x to the kth power. And this is equivalent to a to the k power. And provided it exists. So make a subnote to yourself. That's provided it exists. Okay, now the exponent rule and the logarithmic rule are the next two. So number 8, the exponent rule for limits, obviously. You're going to say where b is a real number and it's greater than 0. So this is also a real number. So in this case, you would say the limit as x approaches a for b raised to the f of x, and that is equivalent to b as x approaches 0, or x approaches a. This is the limit of f of x is the exponent, and that becomes b of a. Logarithmic rule that's rule, not roll. In this case, you would say that for any number b, so you're going to go with 0 less than b less than 1, or you're going to do the value of 1 less than b. You would say that the limit as x approaches a is a logarithmic of base b of f of x. And that is equivalent to log base b of the limit as x approaches a of f of x, which is also equivalent to the logarithm base b of a, and you would say that that is true if a is greater than 0. Okay, and the last rule is number 10. So in number 10, you have the equality rule for limits. So the equality rule for limits says the limit of x as x approaches a of f of x, some f of x, is equivalent to the limit as x approaches a for some g of x And that is true if f of x is equal to g of x for all values where x is not equal to a. Okay, so that's the basics of it. So let me give you some examples and let's work through this. I have a few. Just to give you an idea of how this works. So let's look at example 6. And in your homework, you will have plenty of opportunities to experiment with the answers and get familiar with this. So this is the rules for limits. So we're going to use suppose the limit of x approaches 2 of f of x is equivalent to 3 and the limit as x approaches 2 for g of x is equivalent to 4. And it says use the limit rules to find the following limits. So this is saying, let's find in A, it says, let's find the limit as x approaches 2 for f of x plus 5 times g of x Anybody want to take a guess? F of x is 3. G of x is 4. Nobody wants to take a guess? This becomes
23.
23, because this becomes 3 times 5 times 4, which is 23. Make sense?
It makes sense.
Okay. Okay, in B, they're giving us the limit as x approaches 2. And this is true for f of x over g of x. This is the natural log of g of x. And this part, the top part, is squared. What is it? What do you think that becomes? Remember, f of x is 3 and g of x, the limit becomes 4. You're still approaching 2. So this becomes, this is squared. Equivalent to 3 squared over the natural log of 4. And that gives you 9 over the natural log of 4. Now that becomes 9 over 1.38629. And using a calculator, you get 6.492. Okay, let's take a look at another example. Example 7. So in this one, it says, find the limit as x approaches 3. And you're going to find that for x squared minus x minus 1. All of this over the square root of x plus 1. So what you do here is you start with the limit of x approaching 3 of the numerator, which is x squared minus x minus 1. And this is over the limit as x approaches 3. And you know that is the square root of x plus 1. Which becomes, in this case, if you plug in 3 for the top part, you have 3 squared minus 3 minus 1 divided by the square root of x of 3 plus 1. And so this becomes 5 over 2. And you're nothing. Are you getting this, or are you?
Yes.
Yeah. Okay. Let's look at example 8. In example 8, you have find the limit as x reaches 2. And you do that for x squared plus x minus 6. And you do this over x minus 2. So, well, the first thing you're thinking is, I should be able to factor, and you know you're going to use the quotient rule here, so you're going to do x plus 3, x minus 2 over x minus 2. So this becomes, obviously the limit is x plus 3. As the limit approaches 2, as x approaches 2, this becomes 2 plus 3, which answer should be 5. Easy?
Mhm.
Yep, fairly. Okay, example 9. In example 9, you have the same thing. You have the limit. So find the limit as x approaches 4 for the square root of x minus 2 over x minus 4. So we do this for both. You realize in this case, the square root of 4 minus 2 over 4 minus 4. In the numerator, it gives us 0. And the denominator, it also gives us 0.
That would be a whole, right?
Yeah. So in this case, we cannot use the quotient rule for limits, so what if we use the conjugate rule? Since this is square root of square root of x minus 2 over x minus 4, and we multiply top and bottom by x plus 4. So that becomes x square root of x squared minus 2 squared, and this becomes, oh my god, I used the wrong
Yeah, it should be the square root of x plus 2.
Yeah, sorry. Let me erase this. So yeah, we multiply by the conjugate. Since we have the square root there, we're going to use the square root. So square root of x plus 2 over square root of x plus 2. And now this becomes the square root of x squared
Yes.
and then plus 2 squared minus 2 squared. Oh my god, I'm betting 1,000. This is over x minus 4 times x plus 2, which is going to give us, well, we have to wait to do this one. This is going to give us x minus 4 times square root of x plus 2. So this becomes x minus 4 divided by x minus 4, and this stays as square root of x plus 2. So this final answer becomes 1 over square root of x plus 2. Make sense?
Yes.
And now if we use the rule for limits, we're going to get 1/4, because we're going to get the limit as x approaches 4. And this becomes 1 over square root of 4 plus 2, which gives us 1/4. Oh yeah, that was it for that one. Okay. The next one, example 10. In example 10, we have, again, find the limit as x approaches 1, and that is true for x squared minus 2x plus 1, and this is over x minus 1 cubed. So we're going to start with this becomes x minus 1 squared. This is x minus 1 cubed. So this becomes 1 over x minus 1. So the limit as x approaches 1, in this case, becomes the equality rule for limits. You notice in this case is, if I look at this as a 1 over x minus 1, this becomes, as x approaches 1, this becomes 0. So in this case, it's undefined. Undefined. All right. One second, I'm trying to see where I'm at. Okay, the next example we could do totally. let's do limits at infinity, because I talked about those infinite limits, so let's talk about that. So limits at infinity and this is the limit as x reaches infinity of 1 over x to the nth becomes 0. And consequently, as we reach so the limit as x approaches infinity from the left of 1 over x to the nth, it also reaches 0. And obviously the point is, as it becomes overwhelmingly large or small, it becomes unreachable. So let's look at the limit at infinity. So x is reaching infinity, and this is going to be 12. Let's call this t. Let's call it t squared. So t approaches infinity. So this is 12t squared minus 15t plus 12. And this is all over t squared plus 1. So this becomes, and notice the math here, this becomes really simple. You see how that's t squared and that's t squared, so they're all going to get divided by t squared. So this becomes the limit as t reaches infinity for t squared, 12t squared over, and again, I'm going to emphasize that this is also t squared. This is minus 15t over, again, t squared plus 12 divided by, and this is t squared. And all of this is over t squared plus 1. And both of these are also divided by t squared. So what happens is the t squares reduce. So the limit as t approaches infinity becomes 12 minus 15 over t plus 12 over t squared. And all of this becomes over 1 plus 1 over t squared. So if you think of this, this becomes pretty simple. This becomes limit as t reaches infinity. So this becomes the same thing on the bottom. So this becomes this stays as 12 minus 15 times the limit of t reaching infinity, 1 over t. So this is kind of like a thought, plus 12 times the limit as t reaches infinity of 1 over t squared. And this is over 1 plus the limit at t reaching infinity of 1 over t squared. So this becomes 12 minus 15 times 0, which is the equivalent of this part here, plus 12 times that part, the limit of 1 over t over, and this becomes 1 plus 0. So the limit is actually just 12. It's a lot of jargon for a little bit of math, but it kind of hits the point in the head there. So, all right. The next example is example 12. And in that case, we're going to do the limit as x reaches infinity. And we have 8x plus 6 all over 3x minus 1. So there are several examples here. So in this one, we're going to have example A, which I'm going to call this one A. This becomes 8/3. Quite simply, as x reaches infinity, you have 8x over x plus 6 over x all over 3x over x minus 1 over x. So as you reach this is the limit as x reaches infinity of 8 plus 6 times 1 over x. And this is over 3 minus 1 over x. So obviously what's left is 8 over 3. So you end up with 8 plus 0 over 3 plus 0. Hence 8 over 3. Example B and the solution begins with the limit as x approaches infinity of 3x plus 2 over 4x to the third minus 1. This one becomes 0. Let me explain why. This becomes 3 times 1 over x squared plus 2 times 1 over x cubed over. This becomes 4 minus 1 over x cubed. Okay, so this reduces to 3 times 0 plus 2 times 0. And this is over 4 times 0, 4 minus 0, which leaves you with 0 over 4, which is equal to 0. Okay. The next one. Example C. Here you have the limit as x approaches infinity. This is true for 3x squared plus 2. And this is over 4x minus 3. So this becomes basically 3x squared plus 2 over 4x minus 3. So we're going to divide by This becomes 3x. This becomes times 1 over 2, or 1 over x. This one, the x disappears, and this becomes 3 times 1 over x. So these disappear, and that becomes, as x approaches infinity, the denominator approaches 4, while the numerator, it becomes infinitely large. So therefore, this limit does not exist. And we would say in this case, it reaches infinity. So if you notice, the exponent is larger on the top here. Okay. And for D, we have the limit of, as x approaches infinity, you have 5x squared minus 4x cubed, and this is divided by 3x squared plus 2x minus 1. So they're both the same denominator, and what happens in this case is, let me see, you have, this becomes the limit as x approaches infinity. This becomes 5 minus 4x. This becomes 3 plus 2 times 1 over x minus 1 over x squared. So this approaches negative infinity. Okay, notice that the exponents are the bigger on top, smaller on the bottom. All right, let's look at limits of infinity. So just to sum this up a little bit for you, we have if p of x divided by q of x for a polynomial px and qx, where q is not equal to 0, the limit of x reaching negative infinity and the limit as x reaches positive infinity can be found by the following. By number 1, divide p of x and q of x by the highest power of x and q of x. And number 2, use the rule for limits including the rules for infinity. So in this case, the limit as x approaches infinity of 1 over x to the nth is equal to 0. And the limit as x approaches negative infinity of 1 over x to the nth is also equal to 0. All right. So that's that. So these should be fairly easy to do, I think. Let's talk about continuity, and then we're gonna close to a draw. So continuity. In this case, if I have let me switch pages with you. Okay. If I have what's going on? Continuity. That's weird. All right. In this case, if I have f of x in this case, let's say I have a diagram that looks like such. And let's say I have the going through -1 and I go up to 2, and let's say this is 3, so 2, 1. So, all right. And let's say at 3, I have a hole, and it goes like this. So we would look at this f of x diagram that I've drawn here. And so you would look at it and see that at x is 3, you have a function that does not exist at x is 3. So if I look at figure 2, in figure 2 I have this diagram. So I have two lines. I have a hole here, and it goes this way. 0, here's -1, and I got a hole this way. One line going this way. So in this figure 3, what do I have here? So intuitively, since the graph of figure 2 can be drawn without lifting your pencil at x is 3, it would appear that the function is discontinuous at 3. So in this case, does the function exist at x is 3? In figure 2, if you look at x is 3, it means that this does not exist at x is 3. So it doesn't pass. You have to lift your pencil and draw the open circle in both cases. So in this case, that does not exist. So it's discontinuous. All right. No questions on that?
No.
No, no question. Okay. So let's talk about removable discontinuity. Removable discontinuity. And then there's non-removable. Discontinuity. So in this case, if you look at removable, not removable, versus continuity, we can discuss that. Let me see what else we have so we can Well, it's fairly easy. So let's talk about removable discontinuity and see what happens. So let's do, if you do f of x is equal to the square root of 1 minus x squared. In this case, you would say that this is continuous. And the reason you would say that is because if you drew this on a number line, and this is -1, and this is +1, you would have a solid point, and it would be continuously adding the points. So this is a continuous graph. In removable discontinuity, you can actually eliminate the value. So when the function can be made continuous at a specific point, you can do that by defining or redefining it at that point. So it is removable. So in other words, it's kind of like having an x minus 3. Like let's say you have x plus 2 and let's say you have x minus 3 here. Let's say you have an x minus 3 here. You can remove. It could be removed. Non-removable, obviously, it cannot be fixed. So can't be fixed. And that makes sense. So as an example, again, this one is continuous. And there's no interruption of the function. So let's look at example. Let me see, that was example. God, I don't even know what example I'm on. Let's look at this example. What if I have f of x is equal to 4x minus 3, and this is over 2x minus 7. Is this continuous or not? In this case, is there discontinuity at 7/2? The denominator is the key here. The 2x minus 7 equal to 0 is going to yield you a 7/2. At 7/2, you would say that a is equal to 7/2, and you would say it's discontinuous. Because if you think about it, you can never have a denominator that's 0, right? That makes your denominator, your fraction, irrelevant. Okay. Can you hang in for one more example?
Sure.
Yeah?
Sure.
All right. This is one more example. I promise you, I'm trying to give you everything I have. What if I have e to the 2x minus 3? And this is some g of x. Is this continuous for all x?
I think yes.
It is. If you graph it, so if you graph, let's go with, so it's e raised to the 2x minus 3. Oh no, get back here. Nope. Oh, there you go. It is continuous. There's no interruption. See how it keeps going? Continuous. So in this case, it's continuous for all x values. All right, that is the gist of today's lesson. I have do you have any questions? Anything pending?
No questions.
You know, no. All right, so the next time I see you, we'll capture the next section, which should be rates of change and the derivative, and from there we'll go on to chain rule, quotient rule, product rule, all that stuff. Happy. So, do your best that you can in your homework, and let me know if you have any questions by sending me a text or what have you. I will happily answer you back. No worries. Okay?
Sounds
Thank you.
good.
Toodles.
Have a
Thank
good
you.
night.
Bye.
Bye. Oh my God.